Last episode, we've designed and assembled this tester board here. I've since plugged in that breakout board from Adafruit, which has a FT232H chip on it. That chip translates from USB to all kinds of protocols, including the simple SPI interface that our shift registers use. Now I think it's time that we try to talk to this tester from my computer and maybe also test an actual circuit with it. So let's see if we can establish communication with that Adafruit board. There's a pretty convenient Python library that we can use to talk to all sorts of FTDI chips. So let's install that through pip. Looks like I already have it installed, which is quite convenient. So let's write a Python program to talk to our board. And so we import this PyFTDI library, which is going to allow us to talk to the FT232 chip that's on the Adafruit breakout board. And more specifically, we're going to import the SPI driver as well. So let's establish a connection. So we first create an SPI controller object, which is basically our handle to the SPI specific configuration of this chip. Because the FT232H, it can do all kinds of different protocols, I2C, JTAG, SPI, and has a whole bunch of other protocols it can do. And so if we grab a hold of this SPI controller, it puts the chip in this SPI mode, which is how we are using it. And it gives us an easy way to communicate via that protocol. So all we have to do is configure this controller, and the configure will connect to the board that is attached. Now this is a magic string that the FTDI drivers use, and it's basically a URL as you would find on a website, but it's specific to FTDI chips. What this would allow you to do is, if you had multiple such FT232 chips connected to your system, you could more precisely select which one you would connect to. And if we just have this ::/1 here, this is basically instructing it to just pick whichever the first one is it encounters, because we only have one of them connected. But we could be more clever here. Next up, let's configure a few ports. Now, if we recall from the schematic and the PCB we've designed for this tester, we have this D0 to D7 outputs here, this one side of the Adafruit board. And basically what we've done is D0, 1, and 2, we've hooked up to this SPI interface. And then D4, 5, and 6, we've just used as general purpose input and output. And what we hooked up to it is this store, load, and auxiliary store, which allows us to control the latching of the scan chains that are on the tester board. So we need access to the SPI interface on the one side, and we also want to grab a hold of the GPIOs we have down here such that we can control them. And now these are attached to the D0 to D7 output of the Adafruit board. And then if you take a look at the FT232H, which is the actual FTDI chip that's on that board, if you look at how this is laid out, it has this AD bus output and this AC bus output, which corresponds to the D and the C side of this Adafruit board. And then if we scroll further down and basically check how the pins look like if we use this in the MPSSE mode, which is basically a hardware block in this chip which can drive all kinds of serial interfaces like JTAG, I2C, and SPI. And we're using it in the SPI mode. And if we look at the pin list here, we can see that the serial clock is on pin 13, then data out, data in, and chip select, which we haven't really used. These correspond to the clock, data out, and data in that we've connected here. And then the list goes on to tell us that after this chip select, we have these 4 GPIOs still available on this side. So let's try to get access to these interfaces. So this get port call here gives us access to the actual SPI protocol interface in a sense. We're not using the chip select, so we just set this to whatever the default 0 thing is. And we set the frequency to 100,000 hertz. So that's 100 kilohertz. This is basically how fast the serial clock is going to run. And we'll be able to play around with this later on. But in the beginning, we should just keep it somewhere conservative. And 100 kilohertz seems fairly reasonable expectation of the hardware we've built. And the mode part is mostly interesting if you're using a chip select. And it affects when the FTDI chip samples the data, if it's on the rising and the falling edge. And it turns out that just mode 0, which I think is the default anyway, is good enough and is what most of the SPI chips out there are compatible with. So we'll just roll with that. Now that's the SPI pins. That's the first 3 pins that we hooked up. Now for the GPIO, pretty self-explanatory. So this gives us an SPI object we can use to talk over SPI, and the GPIO object we can use to toggle the pins. And next up, we have to tell the GPIOs whether they're inputs and outputs. And so by calling this set direction function, what we can tell the library is to basically change the direction of the upper 4 bits of the GPIO, so that's pins 4, 5, 6, and 7, and turn these into outputs. And so if we go back to our schematic, basically this hex F0 corresponds to all the upper 4 bits here, the ones we've used as GPIOs, to be enabled as GPIOs and to be outputs so we can drive a value. Now our store, load, and auxiliary store signals are active low signals. So basically in the idle state, we want them to be high. And then when we want to trigger a store or a load, we want to briefly pull them low to initiate that. So after we've set the GPIO direction, let's set the control signals to their idle state. So these 8 bits here, they correspond to bit D0 up to bit D7 on the actual chip. And so the lower 4 bits we have assigned to the SPI interface and we're not using, and then the following 3 bits, they correspond to this store, load, and auxiliary store signals. And so by pulling them high, we're just disabling them. And then let's see if we can control the LEDs we have on the board. Now, these are hooked up to the auxiliary chain, which we have down here. And so basically the auxiliary chain is a 16-bit data word we can shift out, which hooks up to these 8 blue LEDs, which we've arranged in a circle. And then the other byte we have hooked up to the pass and fail LEDs, which is the check mark and the cross. We also have this pull-up hooked up, and then we have this generic output for 4 clock signals that we can individually toggle. And so to shift something into this chain, basically what we want to do is we want to use the SPI interface to shift the data out, and that will make its way through the master out, slave in, and the data will flow through these chips basically in the scan chain arrangement all the way through. And so once we're done, basically once all the data has been shifted out and is now present in these 2 chips, we want to toggle this auxiliary store signal, which is going to copy the data from the internal shift registers, which aren't directly visible at the outputs, and it's going to copy it into the actual output registers, which makes the data visible on the outputs of the chip, and that should also then change the LEDs. Alright, so in theory, we should be able to just write some data on the SPI and then toggle that bit. So this shifts the bytes 0 and 0 out through the SPI interface. And then down here, we are writing to the GPIOs and we're basically disabling pin number 6, which if you recall, corresponds to this auxiliary store signal here. And then immediately after, we're going to pull it back high. So theoretically, at this point here, when this goes low, we should see this data being stored and presented on the shift register outputs. And this will basically update the LEDs to whatever we put in here. So let's connect the board to this computer and run this script. And ideally, what we would expect to happen is, since we're shifting out zeros, is all the LEDs on the board should be off. So let me plug this in. And as you can see, the FT232 chip powers on, and it also powers our board. The green power LED goes on. And then by default, all the LEDs just turn on. This is basically just depending on whatever initial state is in the shift registers here. And so now let's run our program, and we should see the LEDs turn off because we're writing zeros into the shift registers. All right, the script runs through and the LEDs turn off, but the board is still powered. So this is definitely our change. So let's try to turn on a few LEDs. For example, the pass LED, the check mark, is connected to Q1, which is the second bit. Q0 is hidden here on the other side of the chip, which can be a bit confusing. So let's think about how the bytes move through this chain. So when we shift the first byte out of the SPI, it's going to land in the upper chip here. And then when we shift out the second byte, the first byte is going to move from the top chip here into the bottom chip through the serial line here. So after we shifted out the second byte, the lower chip contains the first byte, the one we pushed out first, and the upper chip is going to contain the second byte, which is the one that we shifted out second. And so how this SPI interface works here in the Python API is it takes a list of bytes to shift out. And it's just going to start with the first byte here, shift that out, and then shift out the second one. And so this byte on the left here is the one that gets shifted out first. So that's the one that's going to make it all the way to the bottom chip, which is where we said was the LED check mark. And then in this byte, if we enable the second bit, which is where the LED pass signal is connected, we should see the check mark light up. So let's see if that is actually the case. And sure enough, the check mark lights up. Let's try the red cross and maybe a few of the blue LEDs. So the fail LED, the cross, is just the next bit. It's bit number 2. So it's this one. And let's disable the check mark. And then let's turn on the first 2 LEDs of the circle we have, and maybe the second to last. Pretty cool. So the cross goes on in red, which is this bit here. The check mark goes off, which was this bit that we set back to 0. And then in this circle we have here, the first 2 LEDs in the top right here are on. That's these 2. And then the second to last LED on the left here is turned on. That's this one. Now let's see if we can be a bit more fancy, and instead of just, us writing individual bits here into the numbers, let's see if we can just put this into a loop and then add a small time delay, and let's see if we can have a little animation play on the LEDs. And that way we know all the LEDs are working and we kind of know our way around the Python API here, and we can take it from there. So we have 10 LEDs that we can light up. We have 8 in the circle and then the check mark and the cross. So we want to iterate 10 times. And then let's create a one-hot encoding of this index. This is basically going to enable the ith bit in this number, and there's just going to be 1 bit set. And so we've used 8 of the bits up for the circle. And so we're just shifting down this number here by 8 positions, such that we don't reuse any of the bits that we've used for the circle. And then because the check mark starts at the second bit, we have to shift it back up by 1 position, which if you put it together is just us not shifting it down all the way. And now this would run through pretty quickly, so let's insert a sleep command such that we can add a small delay between each of the steps. Maybe half a second. All right, let's see what this does. Pretty cool. So this walks through all the LEDs we have on the board and lights each up individually, which is pretty neat. Now we're doing a lot of bit fiddling here where we have this bit mask lying around, which is a bit cumbersome. And it would probably be good for the future to package this up into a separate Python class that is easier to work with. All right, so now we can create a tester class and we can give it a few parameters, which are optional. We can specify this universal resource identifier, which is basically telling the driver which of the FTDI chips to use, but we're just going to use the default usually, and we can give it a frequency. And so now here in the configure, we can just use the URI directly. And then down here, we're going to use the frequency directly. And then let's think about how we can deal with the GPIOs in a better way, because we don't want to be toggling bits back and forth here all the time. And so I think what we want to have is a separate function we can call that basically sets the GPIOs to a known value. And so whenever we want to toggle the load or store lines, we just call that function and basically tell that function which of the lines we want to toggle. So let's try to do that. And so we're just going to make it take 3 arguments, load, store, and store auxiliary. And by default, we're going to set these parameters to 0, which is basically going to say, leave these control signals in the inactive state. And so what we have to do afterwards is we basically want to reconstruct this bit pattern here, but instead of hard coding the ones, we want to take them from these load, store, and store auxiliary variables that we've created. So we're assembling this bit pattern. So we start out at 0. This is basically none of the flags set. And then we add each flag onto it if necessary. And so what we're doing is we're negating the load parameter, because if we want to have load inactive, what happens on the board is we want it to be the high voltage because it's active low. So the inactive voltage is high. And so what we do is we take this load here, we invert it such that when we tell it to be false, it's going to be a 1. And then we make sure that it's only 1 bit because this is a Boolean and you never know exactly what Python does in terms of bit patterns and bit magic. So this just makes sure we have a single bit value. And then we shift it up to position 5, which happens to coincide with the load signal here. And then same for store and store auxiliary. Store was bit 4 and store auxiliary was bit 6. All right, and that now is pretty much the pattern that we've manually assembled up here. And we can just write this to the GPIOs. And then up here, instead of using this hard-coded bit pattern, we can just use this function that we created. And so if we don't pass any parameters to the update GPIO function, they all default to false, which is going to mean all the control lines will be in their inactive state. So they're going to be pulled high. Let's also be good citizens and add some documentation here. Let's also ask the Python formatter for its opinion on how we formatted this. So we call the yet another Python formatter in place, everything in the tester folder we're currently populating with the script. And yeah, it inserted a space up here and it thinks this is a better layout, which arguably is true. And then down here, which is our example where we played with the LEDs, what we can do now is actually instantiate such a tester. But now instead of using this tester.gpio, right, to toy around with this, what we can do is we can actually use this update GPIO function now. And in the first instance, we want to toggle the store auxiliary flag. And in the second instance, we want to reset the control lines to their inactive state. This here, updating the GPIOs twice, the first time to enable one of the control signals and then the second time to revert it back to 0. This is probably going to come up quite a few times. So I think we should create a separate function that does exactly this. All right, so that's going to be the helper function that does that for us. And we can just make use of it down here, which is also pretty neat. And now to take things even further is shifting something out of the SPI interface, which makes it appear in all the shift registers, but not yet at their outputs. And then toggling the corresponding control line to actually make it basically copy from this internal shift register to the outputs, which are visible. This is going to be the main pattern how we change the individual bits on this board, not just for the LEDs, but also for the signals that we're eventually going to apply to a chip. So I think this also warrants to be packaged up into a function. So we create this write auxiliary chain function here, which is basically just going to take the data to be stored in these 16 bits that correspond to the aux scan chain that we have on the PCB. And so we're going to make sure that we actually have 2 bytes of data. Then we write out the data and pulse the auxiliary store signal to make the stuff appear on the chips. So now instead of doing this, we can basically use this new write aux chain function. What we might also want to do is immediately after connecting to the tester, we might want to just clear out the LEDs such that they're all off, because the tester can come up in this arbitrary random state. And the same for after the loop has gone through, because after the 10th iteration, we're just going to finish and the last LED that we enabled is still going to be visible. And so if we call write aux chain again, and if we leave the parameters empty, we're just going to use the default, which is just 2 zeros, which is basically turn everything off. And then instead of doing just one run through the LEDs, let's just do an infinite run through them until we're basically asking the Python script to abort. And so with Python, if you abort the execution of the script, it's actually not going to immediately abort, but it's going to throw a keyboard input or keyboard error exception. You can actually intercept that. And so what that does is when we're stuck in this loop and we're basically animating the LEDs, if I hit Control C on the keyboard to cancel out of the Python script, instead of just aborting, this is going to throw an exception, and we can basically gracefully turn off all the LEDs that are visible. So we have a graceful shutdown of whatever we're doing. All right, let's format this and run the script again and see if it still does the same thing on the board. All right, looks like there's a mistake in the script. It's complaining about us calling the update GPIO function on the GPIO object itself. And so that's actually incorrect because this update GPIO function, this is something we've declared on this tester class that we've created, not the GPIO driver that we're getting from the driver library. Let's try again. And there we go, the animation runs. And if I now cancel out of the script, we should see the LEDs turn off instead of just the last one that was lit remaining turn on. And there you go, hitting Control C, basically aborting the Python 3 execution is triggering exception. And the exception we intercept with this try except block here and basically do nothing and just continue with this part down here, which is clearing the LEDs back to 0 again. Now let's think about how we can come up with a better way of turning LEDs on or off than just doing this bit fiddling and basically bitwise logic here and then writing this directly through the auxiliary chain. And besides the LEDs, we also have some interesting control signals attached to this auxiliary chain. We have this pull-up signal that we might want to control, and we have these clocks here that we might also want to toggle and change. So we need a good way to control all of this at the same time. And so I think what we want to do is instead of having some bit magic here and basically having to fully specify what all the bits in this auxiliary 16-bit word are, I think we want a few fields on our tester class where we can basically store what value we want to pull up, the LEDs, the clocks to have. And then we have an update or a flush function that basically takes the configuration we've set in these fields and just flushes it to the tester PCB such that the values become active. So I'm turning this tester into a Python data class, which has a few minor implications, but the main one being we can actually list the fields we want the class to have here at the top. So let's do that. Let's list all the outputs that we've hooked up to the auxiliary chain. So we have the pull up, turn it off by default, pass LED, the fail LED. We have the circle LEDs, which are 8 in total, so we just keep that as a bit mask, because that way we can control exactly how we want the circle to look like. And we have the clocks, which are 4 bits. And so we now have this configuration of the auxiliary chain up here. Let's write an update function that takes this configuration and writes it to the tester. So we have this update auxiliary, and whenever we call this, we basically want to assemble this 2-byte list here programmatically from the configuration that is stored in these fields of the tester class. So we start out with the empty list. Now the first byte here, the one corresponding to this, contains the 2 LEDs right here, the pull-up and the clocks. Again, we take this Boolean value, the LED pass, we make sure it's just a single bit, and then we shift it to the correct position. And if you recall, the LEDs start at bit 1 instead of bit 0, because bit 0 is disconnected here on the other side of this chip. So these are our 2 LEDs. Next up is the pull-up. And the clocks here are represented by an integer value because we basically have 4 clocks, and so we're using the lower 4 bits of this integer to indicate which clock is active. And so by ANDing it with hexadecimal F, which is the lower 4 bits all set, we're basically making sure that we're only taking the lower 4 bits, and then we're shifting them up to position 4 and adding them to this data byte. And so this corresponds to this layout here, where pull-up is bit number 3, and the clocks start at 4, and they go all the way up to bit 7. And then the second byte is trivial. It's basically the thing that gets stored in the upper chip here. And it's basically just an 8-bit value indicating which of the circle LEDs should be on. And so we're ANDing it with hex FF, which is 8-bit set. And this makes sure that if we accidentally configure the wrong value in here, we're actually just going to take the lower 8 bits and store them in this LED circle. Then we can use this write auxiliary chain function that we've written to actually write this data here to the tester PCB. And now what we can do is, remember how we wrote 2 0 bytes into the auxiliary chain right after creating this tester object to turn off all the LEDs and have everything in a known reset state. We can actually do this by default now. So right here, after we have disabled all the control lines, we can actually do the same thing for the auxiliary chain. When we create the tester, these fields here, they come up in this default value of false and zeros. And so if we call just update auxiliary here at the beginning, this is going to do the right thing, basically push an all 0 value into this shifter chain. So we no longer need this here. And now remember how the last time we just walked around this LED circle, lighting each one up individually, and then we had a brief period where the check mark and then the cross would light up. But now that we have these flags in the tester class, it's becoming easier to control the LEDs in a more detailed fashion. And so instead of just briefly lighting up the pass and fail LEDs, what we can do is we can basically say, we're only going to do 8 iterations of this loop. At each step, we're going to light up the corresponding circle LED. And then as long as I is below the value of 4, so the first half of the cycle, we're going to light up the pass LED. And after that, in the second half of the circle, we're going to light up the fail LED. So we no longer need this manual fiddling with the control signals here. We can also make it a bit faster. And then at the end, what we can do is we can basically reset the flags to 0 and use the update function again, so we don't have to fiddle with the auxiliary chain writing. And so, just for fun, when we abort this loop, let's actually turn all the circle LEDs on, so the entire circle lights up after we abort, and then the check mark and the cross, they go off. So let's run this through the formatter and give this a try. All right, now as you can see, we have this spinning circle here on the right. And then in the first half of the cycle, we light up the check mark, and then the other half, we light up this red cross here, and it goes back and forth. And it's a lot more convenient now that we can do these with these individual flags on the field. And now when I abort the script, we should see the entire circle light up, and the check mark and the cross should go off. And there you go. That is pretty neat. So that's us toying around with the LEDs, and I think we've proven that we can write a tester class that allows us to have pretty convenient access to this PCB here. We can use it to connect to it. We can control the GPIOs at a low level manually if we want to, and pulse the store signal and then write to the SPI chain and all that. But more conveniently, for each of the LEDs and to pull up in the clocks, it has a field in the class that we can programmatically just set like you would in any other Python script. And then we have this update auxiliary function, which we can call to basically make the changes we've made effective such that they get flushed out and become visible on the PCB. And so now the next step is to actually test something. We've been toying around with the outputs of this auxiliary chain, but we have the main chains here at the top and at the bottom that we want to interact with, which is where you would connect your DUT, your dot, the design under test. Now let's quickly turn off that circle such that it doesn't glare too much on the camera. Much better. So a while back, I've built this 4-bit multiplier PCB here. It's a very simple circuit. It doesn't have any registers. It's purely combinational. And it has a left-hand side and right-hand side input to 4-bit numbers. And it's going to multiply them here through these adders. And then it's going to produce an 8-bit result here on the output side. And so I think this is going to be an interesting first test case for the tester PCB. So I think what we want to do is we want to hook up the tester outputs here to the left-hand side and right-hand side inputs such that we can apply different values to this multiplier here. And then the result as it comes out of the board, I think we want to bring that down to one of the inputs such that we can read back the value that this board produces in the Python script that we have and can actually check whether it's doing the right thing or not. So first things first, we need power and ground connections, and we have these handy power headers here on the tester PCB, which we can use. And the multiplier is immediately powered. So let's first start with the inputs of the multiplier. Let's hook these up to the tester board, and then let's see how we can control them from the Python script we're writing. So these are outputs 0 to 3. I have to be careful because output 0 on the tester is on the left, but the LHS and RHS inputs are basically in regular notation direction, so the least significant bit is on the right and it increases to the left, just as you would read the number on a piece of paper. Now let's do the same for the right-hand side. Now to make things a bit easier, let me actually not put that right next to the left-hand side output on the tester, but let's shift over a bit and basically use the next header block here, such that we have the left and right-hand side in separate bytes that we will need to shift in. But in theory, there's nothing preventing us from just using the next 4 bits. It's a bit easier to experiment if we do it the other way. All right, so that's our inputs connected to outputs on the tester board. And so if we take a look at the PCB, what I did is basically plug the left-hand side into these first 4 connections here, and then the right-hand side is over here, bit 16, 17, 18, and 19. And so we need to keep this in mind when we shift data out. It's basically in the first byte here, the lower 4 bits contain the left-hand side, and then the next byte we skipped, and then the third byte here, and then the third byte contains our right-hand side in the lower 4 bits. So let's see if we can actually write data to the main shift chain of the tester PCB. Up until now, we have been using this auxiliary chain down here, which is just 2 of these shift registers. But we have this long chain of 8 chips here, each representing a byte, basically 8 outputs on the PCB, that we can shift data into and basically do the same thing as with the auxiliary chain. It's just that we have to toggle the store signal, not the store auxiliary signal. And the data doesn't go into any LEDs, it just gets directly put on these headers and directly driven onto the multiplier in this setting we have here. So I think what we are going to do is we're going to duplicate this pulse store aux function and create a similar one for the regular store. And in this way we can shift data out and then pulse this regular store and have data copied into the output shift registers. And so to write raw output data to the tester PCB, I think we want a function similar to this write aux chain. And so let's call that write output chain. And it's just going to take some data. It's basically a list of bytes, which is the data that we want to have shifted and presented at the outputs of the tester PCB. Now, there's one thing we should consider. The way we have written these Python lists here is element number 0 is on the left, and then element 1, 2, 3, 4, and it basically increases from left to right. However, if you recall how SPI works, the first byte we shift out is going to land in the last chip in the chain. And so this is a bit counterintuitive because if you write a list like this and it has 10 elements, the one on the left is the one that's going to get pushed the furthest through the entire chain. And so in the way we have laid out this board, we have this Adafruit here and its shift data output is basically moving through these shift registers from left to right all the way over to the right edge of the PCB, at which point the data goes into this expansion header, and if we have a second board attached, it's basically going to move into that board. So in a sense, the first byte that leaves the Adafruit, the first byte we shift out, is the one that's going to move the furthest away to the right in this whole chain. And complementary to that, the last byte we shift out here is the one that's going to end up right here in the leftmost shift register and correspond to our leftmost data. And so what this would mean here, if we have a long list of data, is that the leftmost element would end up in the rightmost place on the actual physical board. And the last element in the list, which is the rightmost in how you would read it and look at it, is going to end up in the leftmost position of the board, basically the one that's closest to the Adafruit, because it's the last thing that gets pushed out. And so I think to make this more convenient to work with, I think we want to reverse the data here before we shift it out over SPI. And that way, from your perspective as the programmer, the data you give to this function is going to appear in the same order on the actual physical hardware. So your element on the left is going to be flipped around. It's going to be the last element shifted out, and conversely, when that is shifted out onto the hardware, it's going to end up in the leftmost location. So the way you read the list here is also the way how it will appear in hardware. And getting these small things right is pretty crucial because you're doing debugging and testing with this tester PCB. And so you want to eliminate as many sources of bugs and misunderstandings as possible so you can focus on the thing that is actually not working. And it's pretty unhelpful if you constantly have to think about whether you need to look at the first or last element in a list to know which corresponds to which location on the actual hardware. So this comment tries to clarify that. All right, and technically this should be all that's needed to write some data out into the main output chain. And so let's give this a try. Let's get rid of this LED example here. And we're going to start out with a data array with 8 0 elements, which corresponds to the 8 bytes or the 64 bits, the 64 outputs that we have on the tester PCB. And then let's actually apply some data to the left-hand side and the right-hand side inputs. Now, if you recall, the left-hand side is connected to output 0 and up on the tester board, and the right-hand side is connected to output 16 and up. So that corresponds to data being in byte 0 and data being in byte 2. One thing I think we want to do is visualize how these data bits here in the Python script translate to the individual output bits on the PCB. So let's write the print function that takes such an 8-byte array and turns it into a representation of how this looks like in the physical hardware implementation. Let's call it something like print blocks. And it's going to take some prefix just to make printing and reading easier, and then the actual data that we're shifting out. And so we go through each byte in the data and we format it. And so in this format bits function, what it does is it takes one single byte and it basically produces the ones and zeros as they would appear on the output pin header of the tester PCB. And the reason why we have a manual implementation of this and not use the Python standard function to do that is that the least significant bit number 0, is on the left on the PCB. So that's the thing we want to print first. And then as we go to the right, we want to see the more significant bits. And the standard Python printing function does it the other way around. And then once we're done with formatting the bytes, we basically have a list of strings, and each string is 8 characters wide and corresponds to the outputs on that specific part of the header. And now we want to print the blocks in 2 lines. So we print the prefix that is configured, and then we're going to take all the even bytes and print them with a space as a separator. And on the second line, we have the prefix again, and then we take all the odd bytes and print them with a space in between. And this should provide output that visually lines up exactly with how things are going to look on the tester PCB. So let's see if this prints something useful to the terminal. It does. This looks pretty good. So the first byte, the one up here, you can see we have set to 1001. This is where the LHS is connected. Byte number 1 we have skipped. Byte number 2 is the one where RHS is connected. And then in the lower 4 bits here, we have a different pattern, 0110. And now all that's left for us to do is to actually write this to the main output chain and see what happens. Let's give this a try. Pretty cool. And so as you can see, the left-hand side has the pattern 1001. This corresponds to what we see on the terminal and what we have configured in the Python script. And then the right-hand side is the pattern 0110, which also matches what we've configured. And then there's a corresponding output coming out of the multiplier. Now, the natural next step is to actually take the result that the multiplier produces and feed that back to our tester PCB such that we can look at it and check that it's doing what we want. So in order to read data back from the design we are testing through these tester inputs down here, what we have to do first is trigger a load by toggling the load wire that we have. And that's basically going to instruct these shift registers here to copy the data at their inputs into their internal shift register. And once the data is in that internal shift register, we can just perform an SPI read to shift it all the way through to the Adafruit and have it returned by the SPI driver. So I think we want, again, another one of these pulse signals, but this time for the load. And then in addition to writing the output chain, we now also want to be able to read the input chain. So first we pulse the load signal. This will copy the data, the inputs of the shift registers into their internal actual shift register. And then we do an SPI read to shift the desired number of bytes out of that chain and have it returned as, again, a Python list of bytes. Notice that we don't do any reversal of the data here. And the reason for that is that the direction in which we shift is reversed for the input chain in contrast to the output chain. And every clock cycle, the data shifts closer to the Adafruit breakout board. And now the data that is in the shift register that is the closest to the Adafruit breakout board, which in our tester PCB is the input number 0, is also the one that's going to be shifted out first. And so this is going to land in the first index in this Python array that we get back. And then as we keep shifting, we keep filling in the upper bytes in this list, which correspond to the data that is further and further away from the Adafruit breakout board. And so in theory, that's all that's needed to read data back from the tester PCB and get it back into our Python script. And so down here where we test the 4-bit multiplier, we can have a section where we first set the outputs of the tester PCB, which is configuring the left and right hand side inputs of the multiplier. And then we can add a read input section where we just read back whatever the multiplier produces and we print that out to the console. So let's run this and see if we can read back the value that the multiplier is producing at its output. All right. So here in the first two lines, you can see the data that we're outputting. This is the same as before, but now we have this read data input here, which is basically showing whatever we read back from the design under test, which is the multiplier in this case. And now in the bottom right here, we can see a bit pattern, and the location corresponds to this bottom right part of the rightmost input header down here. And this is where we hooked up the multiplier's output. Keep in mind that the multiplier produces the least significant bit on the right and the most significant bit on the left, as you would read it on a piece of paper. But we've connected the least significant bit to bit 0 of the input, so it's the leftmost bit here. So this appears reversed in how we look at it in this printout, because we are trying to match how the bit arrangement is on the tester visually. And so you can see that the least significant bit is 0 here, and then we have 2 1s, a 0, another 2 1s, and then 2 zeros. And this is exactly the pattern we are reading back. So let's change the number we are inputting to the multiplier. Let's maybe set this bit here. And let's rerun. Now, as you can see here, this number changed. This bit that we've just configured has been set, and you can see on the actual PCB, the corresponding bit lights up now. And then the output we read back has changed accordingly, and so has the output of the actual multiplier. So now we have the 0 followed by 3 1s, followed by 2 zeros, a 1, and a 0, which is exactly what shows up here in our script output. Now, if you recall, we also have this pull-up line that we have connected to the auxiliary chain. And so this pull-up line here is connected through resistors to each of the input bits. So if we set the pull-up bit to 0, the resistors act as a pull-down, and the inputs, if left unconnected, are getting pulled down to ground. And then if we set the pull-up output to high, these turn into pull-up resistors, and the inputs to the tester PCB will get pulled high to VDD. And we can make use of the fact that these are just pull up and pull down resistors. So they're fairly weak. And if something is connected to an input, it's easily overriding and overdriving whatever the value is that the pull up wants to have the input go to. But if we leave an input unconnected, it's definitely going to assume the value of the pull-up bit. And so when we read this piece of data in here, the pull-up was disabled, which you can see all the way up here at the beginning of our script. We're setting pull-up to false, and we're actually never changing it. So now instead of just doing a single read from the input chain, let's do 2 reads with different pull-up settings. And so now instead of doing the read directly, what we do is first we do a read with the pull-up. So we enable the pull-up and then flush this change to the tester PCB. And so after this call, the pull-ups are enabled and will pull the inputs high if they're unconnected or have a high impedance connection. And then we do our read and we declare this the data as seen when the pull-up is active. And then we do the same thing for a pull-down. We disable the pull-up, update the pull-up output bit on the auxiliary chain, do another read, and we declare this the data as seen when the pull down is enabled, and we're printing both of them. So let's see what output this produces. All right, so we have this first block here, the in1, which is basically where the pull-up bit is 1. And as you can see, all the unconnected inputs have been pulled to this pull-up bit value, which is a 1. But the value in the bottom right here, which is where the multiplier is connected, the one that is actually driving, has the value we expect. And then during our second read with the pull-up disabled, we can see that all the disconnected inputs here, they get pulled to this low value that we've configured. But again, the actual multiplier output stays the same. And so we can use this discrepancy between the read under pull-up and the read under pull-down to determine which of the inputs are actually disconnected or are high impedance. And if you look at this in more detail, whenever the bits agree in both reads, we assume that this is a strongly driven input and there's a driver attached to it that is able to overpower the pull-up resistors. However, when the bits differ between the reads, this is a strong indication that the input is disconnected. And so let's actually update this print blocks function a bit to make use of this information. So instead of just accepting 1 byte array, we're going to accept 2, one with the pull up and one with the pull down. And so again, we are iterating over the bytes, but this time we iterate over pairs of bytes. And then what we do is we call this format bits function that we have here with just one of the bytes. And then as the second argument, we actually take the exclusive OR of the 2 values that we've read. And what this exclusive OR does is it produces a 1 whenever the value in A differs from the value in B, or it produces a 0 when both of the values agree. And so we can go and tweak the format bits function accordingly, where we now say the value to print is the first one we pass in, the byte. But then we have this Z input, which is basically indicating which of the bits in this byte are high impedance, because the XOR has detected that depending on whether we pull it high or low, the input will read a different value and so is likely disconnected. And so before we print an actual value, we check this Z input to see if we have detected a high impedance state, a disconnected input. And if we did, we're just going to print it as a Z in the output pattern and not as a 1 or 0. And so instead of printing these values like this with the pull up and the pull down separately, we're just going to pass the 2 values we've read, the one for the pull up, the one for the pull down, into this print blocks function, which is then going to do the right thing. And so let's run this again. Forgot to update this use of print blocks. We're just going to pass it twice this data input because there's no discrepancies we're interested in. So if we pass in the same data, there's never any discrepancy to be detected. Try again. And here we go. So as you can see, these 2 separate reads here, we've now combined into a single output, and we're using this discrepancy detection between the first and the second read to basically indicate where the high impedance states are. And so all of the inputs that we have disconnected in actual physical hardware, read as a Z, as a high impedance input. And the only thing that shows up as actual proper ones and zeros is the multiplier output, which is the one we've actually connected. And so what we can do now is we can connect some random inputs on the tester PCB to VDD and ground and actually see them show up. And so I connected 2 jumper wires here to VDD and ground. These are going to be these 2 bits here. So let's rerun this command. And as you can see now, these bits show up as strongly driven, as connected, because they're tied to VDD and ground directly. So this is going to make testing and working with the tester pretty convenient, because we can actually see if something is disconnected. This might be unintentional because the user forgot to connect something to the device under test, or something got disconnected or knocked loose. So this is a way to detect that. But also if you have devices that have an output enable and can actually be in a high impedance mode if they're not selected or the output is not enabled, this gives us a way to actually detect this and test for this specific situation. And so we can actually not only check if a buffer does the right thing in, just passing data through, but we can also test the buffer's output enable signal and detect if the buffer indeed releases its output when it's instructed to do so. So let me get rid of the jumper wires again. So rerunning it puts us back in the situation we were in before. So we've played around with setting different input values on the 4-bit multiplier, and we've also made sure that we can read back its output value and also detect when a signal is disconnected. So now I think as a next step, we might actually want to start checking if the multiplier itself is doing what it is supposed to do. So actually testing the hardware that we have attached to our tester board. So instead of using these fixed values here, let's actually pick some inputs as a decimal number. Let's say 7 and 12. Now let's actually make sure that the multiplier itself is doing the right thing. And so the first thing we might want to check is basically a continuity test or a connectivity test, where first, before we check the multiplier, we check if it's even plugged in. And so again, we use the fact that an unconnected input will show up as the pull up and pull down readbacks being different. And so first we assert that the 2 values are actually the same. So there's a strong drive on this input that we're measuring. And then let's compute the expected value that we want to see from the multiplier. That's just A times B. And then let's extract the actual value that the multiplier itself is producing. And then let's check if these match. We probably want to increment some counter that counts the number of mismatches we've observed. We're just doing 1 test now, but if we run multiples, we probably want a summary which indicates how many tests failed. Let's actually initialize this to 0 here at the top. And then let's print a message which shows what we applied to the multiplier, what it actually returned, and what we expected it to return. So basically what we're doing is we're printing the value A, that is the left-hand side input, as a 4-bit binary number with leading zeros, and then the B input as a 4-bit binary, and then the actual value coming back from the chip as an 8-bit value, and in parentheses the expected value that we have computed and that we want to see. Next to that, we're going to print the same thing, but with decimal numbers, which are a bit easier to read, and it's easier to quickly verify that the thing is doing what it is supposed to do. So let's give this a try. And so as you can see, we get a line printed out from our script, which basically says what the A and B values are. These correspond to what is visible on the LEDs that the multiplier has. Then we see the result from the multiplier hardware, which is exactly the pattern that we also see on the LEDs. And then in parentheses, it's the expected value that we wanted it to have. And then on the right here, it's basically just the decimal representation of this. And so 7 by 12 is indeed 84. And we computed that we would like to see 84. So the hardware is doing the right thing. Now let me disconnect one of the bits of the multiplier to simulate that it got knocked loose or not connected properly. And so if we run the script again, we actually get an assertion because there's this Z here in the input, which is the rightmost bit that I disconnected in hardware. We're actually checking for that in this assertion. And so we get this assertion, which basically asks us if the output is properly connected. And so this is a good indication for us to go back in and actually check if the connections are properly made. Let me connect that disconnected bit to VDD so it reads back as a 1. And as you can see, the assertion is no longer there because we actually have something driving that pin. However, it's the wrong thing. If you look at the right-hand side here, it's saying we're expecting an 84, but we actually received a 212 from the multiplier. And so these bit patterns here are also totally different. Now, it's a bit difficult to actually see that there's a discrepancy here because it's all just text in the terminal. So let's make use of a few colors here in the output. We're going to use the term color package, which is pretty popular and common, and it has this colored function that we can use. And so now instead of directly printing the actual values here, we can actually format them and colorize them a bit before we print them out. So this would print the value in blue, which it does, but that doesn't really help us yet. What we want to do is actually determine the color of how this gets printed based on whether the actual output that we're reading matches the expected output. So we're going to print in bold red if the actual output doesn't match the expected output, and otherwise just regular green. Now instead of hard-coding the blue color here, we're just going to use the color and the attributes that we've determined above. And let's give this another try. And as you can see now, the discrepancy gets highlighted. We actually get the bit pattern that is wrong in bold red, and also the decimal value here that is wrong in bold red. And now we also have this check mark and the cross here, the pass and fail indicator LEDs on the tester PCB. And I think what we want to do is at the end of our test, we want to set these LEDs to reflect whether all the tests were successful or we have detected some discrepancies. And so if you recall, we have these LED pass and LED fail flags here, which we can just change and then call the update auxiliary function to actually make them appear on the tester PCB. And at that point, we also want the Python script to abort with an error message and an error exit code such that we can detect that something went wrong. Let's give this a try. All right, we see a mismatch here in the terminal output where we see the exact bit patterns that fail, and we get an assertion error. The Python script aborts, and it basically tells us that there's one mismatch, and we get a non-zero exit code. So we can tell when we call this script from any other process, we can actually tell that something went wrong during testing. And then last but not least, the red cross here on the PCB lights up to indicate that we have this discrepancy here. So let's restore functionality again. And let me rerun this test. And as you can see, the green check mark appears. And in our terminal, we see that the actual output is now in green because it matches what we expect to happen. So this is basically applying a single pair of input values to the multiplier and checking that for that specific case, the result it produces is correct. So in a sense, it's spot checking that particular input pattern and checking whether it produces the correct output pattern. But now if you think about it, the multiplier only has two 4-bit numbers as inputs. So there's only 256 different combinations of the left and right hand side bits that we can actually feed to the multiplier. And running through just 256 combinations of something doesn't sound like it's going to be a lot of work for a Python script and this tester PCB we have attached here. So instead of picking a single input value up here, we are going to loop over all the input combinations. So we're looping over all of the 16 possible values for A, and for each of those we're going to again loop over all the possible values in B and test that specific combination. And so all we do is we nudge this to the right, so it's part of this loop here. And then we don't need to pick the inputs manually at the beginning. So this is going to run over all 256 combinations. But we also have that LED circle on the tester PCB. And I think what we can do is, because we have 8 different LEDs, we can basically show the circle slowly filling up as we progress through these test cases, such that we can look at the tester board and actually see how fast the test is progressing. Now this is a handy little trick here to basically create a number which in binary has a certain number of lower bits filled with ones. Let's give this a try. That is pretty cool. The output is a bit noisy and the circle lights up at the end. Let me change that. So we no longer need to print the intermediate raw data we read back. And let's reset the circle to being off at the very end. Let's run this again. And we also don't want to display what we're outputting. So let's run this again. This is pretty cool. So as you can see when I run it, the circular progress bar we have on the tester is actually showing the progress through the tests. And then in the end, the check mark lights up to indicate that all the patterns were correct. And then if we look at the terminal output that our script produces, we can basically see that it's running through all the input patterns, which is the first 2 numbers here. It's reading the result. It's comparing against what it expects the result to be by basically doing the multiplication on the computer that it's running on and showing a summary. And we can scroll through the entire list here and basically look at all the combinations here. And so that's 256 patterns tested. And in this case, since this is a 4-bit multiplier, it's actually a complete and exhaustive test. We have tested every single piece of functionality. This is not going to be possible for hardware in general because the number of different combinations of inputs grows drastically as the number of inputs increases. And as soon as you have registers in the circuit, it becomes very complicated. But this is a good starting point. Now, one thing that is going to be an interesting test is let's actually simulate that something is wrong with the multiplier. For example, we could say that the least significant bit of the output has a solder bridge to the second least significant bit in the output. And so these always show the same value. So let me connect the least significant bit here to its neighbor to simulate that. And so let's rerun the test. And as you can see, we get a red cross now because something went wrong. If we look at the terminal output, we can see that there's 96 mismatches now. And we can actually scroll through the list here and we can see every single pattern that showed a problem. So let me restore the correct functionality. If I leave it disconnected, we still get this assertion about the multiplier output being disconnected. And if I plug it in properly, I can rerun the test and we're back to a green check mark and also the console output is happy. Now this is basically the wiring problems we might encounter where neighboring bits are stuck at the same level because they are physically connected through a solder bridge, for example, or things are disconnected because a solder connection has come loose or we forgot to plug in a wire. But now let's think about a different problem. What if the hardware is actually functionally not doing what it is supposed to do? So instead of a multiplication, we might actually be looking for an addition. And we expect to have implemented an addition in hardware. And so let's do a run of that. And so the output is vastly different now. It's basically showing almost everything as a failure because the hardware is not nearly doing what we expect it to do. If you have these single bits being accidentally connected or being off, you usually end up with only a few or a certain subset of the patterns being wrong because a lot of other things still keeps working. But here we're basically talking about either doing multiplication or addition, which are 2 very different things. And so interestingly, there's 254 mismatches. So 2 patterns actually ended up matching. And if we scroll further up a bit, we can see one case where addition and multiplication are actually the same is if both inputs are 2, in which case we get a 4, which is kind of cool. And the other case is the trivial case, 0, it's just 0 under addition and multiplication. So let's fix this back, because we actually expect it to be a multiplication. And the board is green again. All right, I'm very happy with how this works. Having such a tester board is going to be very, very useful for testing PCBs that we're building, especially if we're building the PCBs for the CPU, where we might build things like a register file or an ALU or certain pieces of the decoding logic for the instruction decoder. It might be a good idea to actually build up that specific circuitry and then individually testing it by hooking it up to our pattern tester here. And so if the number of inputs is small, we can do an exhaustive search where we just run through all the combinations. Another alternative that is pretty popular is to do random testing, where instead of going through all the combinations of inputs, we're actually picking random numbers for the inputs. And we have a model somewhere in software, for example, written in Python, like we did the A times B here. We have such a model, and what we do is we feed these random inputs that we've picked, we feed them to the hardware and read back the result. And we also feed it to this Python model that we have and look at what it thinks the hardware should produce. And then we compare the two, and that's going to indicate if our hardware does the right thing or not. And so this notion of having a piece of hardware run and then have a piece of software basically be a programmatic description of what the hardware is supposed to be doing, that's called golden model testing, where the thing we have in software is called the golden reference model, which someone has written up, and presumably it was easier to write that thing than to come up with the hardware, because for example in Python it was trivial to just type the star operator to mean multiplication, but the hardware was pretty difficult to assemble because you need these adders, you need these AND gates, and you need to mask certain things out. And so with this golden model testing, what we're hoping is that we have a description written in software that is a lot simpler to get right than the actual hardware. And we can test this software implementation pretty easily and then verify that the hardware that we've built actually does the exact same thing. And so in the future, when we come up with new PCBs, new hardware designs, we can actually write small Python programs that just run through a few interesting input combinations and check the result, or depending on the complexity of the circuit, we might run through all the input combinations instead. There are also more clever approaches to do this. It's also generally useful to read a file from disk, where each line in the file corresponds to the things to apply to the design on the test, and then what we expect the design on the test to return. And these files are usually called test vectors or test patterns. And so this is generally called pattern testing, where you're preparing a certain list of interesting pattern to apply to your circuit. And then you have a program which basically just runs through the list, applies your patterns, and then checks whether the outputs match what you're expecting. And there are a few pretty clever algorithms for the case where you have a description of how your hardware looks like. So you have a description of your AND gates, your OR gates, your chips, and how they're connected. There are algorithms to systematically find certain classes of mistakes that can happen and that can detect those. And in the future, we might get around to actually toying around with something like that. But I think this is good enough for now. And for most PCBs that we want to test in the near future, it's actually going to be sufficient if we can just write a Python script and apply some interesting inputs and check for the outputs. So this has been a lot of fun. It's pretty cool to have such a user interface on an actual PCB. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.